Look up. On a clear day, really look up. You'll see them. White lines scratched across the blue, as if somebody took a piece of chalk and dragged it slowly from one side of the sky to the other. Some of them are thin and sharp. Some are fat and fuzzy. Some vanish in a few seconds, like a breath on a cold window. And some of them stay. They spread out, they get wider, they blur into a haze, and hours later you look up again and the line is still there, wider now, smeared across half the sky, and the plane that made it landed 3 states away an hour ago. What is that? What is a plane leaving behind it? And why does it sometimes last longer than the flight itself? Let's start with something you already know. You've done it yourself. Stand outside on a cold morning in January. Breathe out. What happens? You see your breath. A little puff of white appears in the air and then fades away. You know what that is. It's water vapor. The air coming out of your lungs is warm and moist. When it hits the cold air outside, the moisture condenses into tiny droplets of liquid water. Little droplets scatter light in all directions, and that scattering is what makes the puff look white. Then the droplets evaporate back into invisible water vapor, and the puff disappears. Simple enough. Nothing mysterious about that. You've known this since you were 5 years old. A jet engine, at its core, is doing the same thing. It's breathing. It takes in air, mixes it with fuel, burns it, and exhales. And that exhaust is hot and moist. The burning of jet fuel, which is mostly kerosene, is a chemical reaction. You're combining hydrocarbons with oxygen. And 2 of the main products of that reaction are carbon dioxide and water. For every kilogram of jet fuel you burn, you produce roughly 1.2 kilograms of water vapor. That's a lot of water. A large commercial jet burns something like 2,000 to 3,000 gallons of fuel per hour. That means it's pumping hundreds of kilograms of water vapor into the air every minute. Now I want you to appreciate something about that number. 1.2 kilograms of water for every kilogram of fuel. That means the exhaust actually contains more water by mass than the fuel that produced it. How can that be? Because the hydrogen atoms in the fuel combine with oxygen atoms from the air. The fuel supplies the hydrogen. The atmosphere supplies the oxygen. And together they make H2O, water, which is heavier than the hydrogen alone. So the engine doesn't just convert fuel into exhaust. It grabs oxygen from the atmosphere and combines it with the fuel to create something new. The atmosphere is an ingredient, not just a medium. That's a subtle point, but it matters, because it means the engine is doing something more intimate with the air than just pushing through it. It's chemically transforming it, so the jet engine breathes out hot, moist air. And the air up where jets cruise, at around 30 to 40,000 feet, is cold. Brutally cold. -40, -50, -60 degrees. At those temperatures, the moisture in the exhaust condenses instantly, just like your breath on a January morning, but vastly more dramatic. But wait, let me complicate even this simple story a little, because it's not just the moisture in the exhaust that matters. The exhaust also heats the surrounding air. Hot gas mixes with cold gas. And whether a contrail forms depends on the competition between 2 effects: the addition of moisture, which pushes the air towards saturation, and the addition of heat, which pushes it away from saturation, because warm air can hold more water vapor without condensing. There's a physicist, a German meteorologist named Ernst Schmidt, who worked this out rigorously back in 1941. And independently, a fellow named H. Appelman in the United States did the same analysis in 1953. They showed that you can predict whether a contrail will form by drawing a line on a graph of temperature versus moisture content. The exhaust starts hot and moist. As it mixes with the cold ambient air, its temperature drops and its moisture content changes along a straight line on this graph. If that mixing line crosses through the region where the air is supersaturated, meaning there's more water vapor than the air can hold, then condensation occurs and a contrail forms. If the mixing line stays in the unsaturated region the whole time, no contrail. This is called the Schmidt-Appelman criterion, and it's elegant. It reduces the whole question to geometry on a graph. And it tells you something useful. Whether a contrail forms depends on three things: the temperature of the ambient air, the humidity of the ambient air, and the properties of the engine exhaust, specifically how much water and heat it produces per unit of fuel burned. The colder the air and the more humid it is, the more likely you are to get a contrail. Below a certain temperature threshold, roughly minus 40 degrees, contrails form almost inevitably, regardless of humidity. The exhaust is just too moist, and the air is just too cold for the mixing line to avoid the saturation region. So that's the answer. The white line is condensed water. The technical name is a condensation trail, which got shortened to contrail. And the basic mechanism is exactly the same thing that happens when you breathe out on a cold day. Hot, moist air meets cold air. Water condenses. You get a visible trail. All right, so that's obvious. But let me ask you something. If it's just condensation, why doesn't every plane leave a contrail all the time? You've noticed this. Sometimes a plane crosses the sky and leaves a bold white line. Sometimes an identical plane crosses the same sky and leaves nothing. No trail at all. Clean as a whistle. What's different? And here's where it gets interesting. Because the answer is not about the plane. It's about the air. See, condensation alone isn't the whole story. Your breath on a cold morning condenses, yes, but it also evaporates almost immediately. The droplets form and then they're gone. If the air around them is dry enough, the droplets give up their water back to the air as vapor, and the visible puff vanishes. This happens in a few seconds at most. The same thing happens to contrails. The exhaust comes out, the water condenses into droplets, and then the question is, does the surrounding air let those droplets survive, or does it suck the water back out of them? That depends on a single property of the atmosphere at that altitude: humidity. Specifically a quantity called the relative humidity with respect to ice. At cruising altitude, it's so cold that water doesn't really exist as liquid droplets for very long. The droplets freeze almost instantly into tiny ice crystals. And once they're ice crystals, the relevant question changes. It's no longer about whether the air is humid enough to sustain liquid water. It's about whether the air is humid enough to sustain ice. There's a critical threshold. If the air is supersaturated with respect to ice, meaning the relative humidity with respect to ice is above 100%, then the ice crystals can survive. They don't evaporate. In fact, they can grow. They can attract more water molecules from the surrounding air and get bigger. When this happens, the contrail persists. It stays in the sky. It can last for hours. But if the air is subsaturated with respect to ice, if the humidity is below that threshold, the ice crystals slowly surrender their water molecules back to the atmosphere. They shrink. They vanish. The contrail evaporates, usually within a minute or two, sometimes within seconds. And this is the part that amazes me. The difference between a contrail that vanishes in 30 seconds and one that persists for 6 hours is not a big difference. It's not like the air needs to be 10 times more humid. The threshold is sharp. Just above saturation, the crystals survive and grow. Just below, they evaporate and die. A tiny change in humidity, a few percentage points, can be the difference between a trail that's gone before you notice it and one that's still visible at sunset. This is a phase transition behavior. The ice crystals are right at the boundary between survival and extinction, and which side of the boundary they fall on depends on conditions that can vary over distances as small as a few hundred meters. You can have a pocket of supersaturated air sitting right next to a pocket of subsaturated air with nothing visible to mark the boundary between them, until a plane flies through. Then the boundary becomes visible, because the contrail appears in one pocket and disappears in the other. The plane is an invisible ink revealer for atmospheric humidity structure. So the difference between a contrail that vanishes instantly and one that lingers all afternoon, is not the engine. It's not the fuel. It's not the altitude, though altitude matters because it affects temperature. The primary factor is the humidity of the ambient air at that specific altitude, and that humidity can vary enormously over short distances. You can have a pocket of very humid air right next to a pocket of very dry air, and a plane flying through both will leave a trail in one and none in the other. You've seen this. A plane crosses the sky and the contrail appears, then disappears, then appears again, as the plane passes through patches of air with different humidity. The plane didn't change, the sky did. That's the second layer. The first layer was hot, moist exhaust meets cold air. The second layer is whether the trail survives depends on the humidity of the air the plane is flying through. Simple enough. But let me show you another layer. Those ice crystals in the contrail. Let's think about what they actually are. When the exhaust first comes out of the engine, the water vapor doesn't just condense on its own. It needs something to condense onto. In physics, we call these condensation nuclei, or if we're forming ice, we call them ice nuclei. They're tiny particles that provide a surface for water molecules to grab onto and start building a droplet or crystal. Your breath on a cold day uses dust and aerosol particles that are always floating around in the lower atmosphere. There are plenty of them near the ground. Pollen, sea salt, bits of soil, combustion soot. The air near the surface is full of these little seeds, but jet exhaust provides its own. When kerosene burns, it doesn't just produce carbon dioxide and water, it also produces tiny particles of soot. These soot particles are extremely small, on the order of 10 to 50 nanometers, and they come out in staggering numbers. A single jet engine can emit something like 10 to the 15th soot particles per kilogram of fuel burned. That's 1,000,000 billion particles per kilogram. These soot particles are perfect condensation nuclei. They have the right surface chemistry, the right size, and the right properties to attract water molecules. And it's worth understanding why soot is so good at this. A soot particle is essentially a tiny ball of carbon produced by incomplete combustion. Its surface is rough at the molecular level, full of nooks and crevices and chemical groups, hydroxyl groups and carbonyl groups that are attracted to water molecules. The water molecules land on the soot surface and are held there by intermolecular forces. More water molecules arrive and pile on top. A tiny liquid shell forms around the soot particle. And because the shell has a curved surface, and curved surfaces have interesting thermodynamic properties, there's a size threshold the droplet needs to exceed before it becomes stable. Below that threshold, the droplet evaporates. Above it, it survives and can keep growing. This threshold is described by something called the Kelvin effect. And for the soot particles that jet engines produce, the threshold is easily reached because the exhaust is so rich in water vapor. So what happens is this. The exhaust comes out. It's full of water vapor and full of soot. The water vapor condenses onto the soot particles first, forming tiny liquid droplets around each soot particle. Then, because the temperature is so far below freezing, those droplets freeze into ice crystals within a fraction of a second. Each ice crystal has a little soot particle at its core, like a pearl forming around a grain of sand. Or maybe a better analogy, like a candy-coated chocolate, where the chocolate is soot and the candy shell is ice. Except the shell is made of trillions of water molecules arranged in a hexagonal crystal lattice, and the whole thing is smaller than the width of a human hair. And now the contrail is not just water. It's a line of trillions upon trillions of tiny ice crystals, each one wrapped around a speck of combustion soot, strung out in a line behind the aircraft. It's a cloud, a very long, very thin, very artificial cloud. Let me ask you the next question. If the contrail is a cloud, does it behave like a cloud? Yes, it does. And this is where things start to get profound. A persistent contrail, one that forms in humid air and doesn't evaporate, begins to spread. Wind shear at cruise altitude pushes the trail sideways and stretches it. Turbulence mixes the ice crystals outward. The trail gets wider and wider. Over the course of an hour or two, what started as a line a few meters across can spread into a band a kilometer or more wide. And as it spreads, it begins to look less and less like a contrail and more like a natural cirrus cloud. Let me describe this spreading in more detail because it's physically fascinating. At cruise altitude, the wind speed and direction typically change with height. This is wind shear. The air at 36,000 feet might be blowing from the west at 80 knots. The air at 37,000 feet might be blowing from the west-northwest at 90 knots. This difference in speed and direction at different heights stretches and tilts the contrail. The crystals at the top of the trail get carried in a slightly different direction than the crystals at the bottom. The line smears out. Meanwhile, turbulent eddies, swirling pockets of air that are always present in the atmosphere, mix the ice crystals horizontally. These eddies are like invisible spoons stirring the crystals into the surrounding air. Small eddies mix on a scale of meters. Larger eddies, driven by atmospheric waves and instabilities, mix on a scale of kilometers. Over hours, the combined effect of wind shear and turbulent mixing transforms a narrow line into a broad, diffuse sheet. There's also a self-reinforcing process. As the contrail spreads and thins, the ice crystals at the edges find themselves in ambient air that may be ice supersaturated. They grow by collecting water vapor from this ambient air. New crystals can even nucleate on aerosol particles that are naturally present in the upper atmosphere, particles that wouldn't have formed ice on their own, but can do so in the slightly modified conditions near the contrail edge. The contrail seeds its own expansion. It's not just spreading passively. It's actively recruiting water from the surrounding atmosphere and converting it into cloud. Cirrus clouds are the high, thin, wispy clouds you see at high altitude. They're made of ice crystals. They form naturally when humid air at high altitude cools past the saturation point. And persistent contrails, as they spread and age, become essentially indistinguishable from natural cirrus. They have the same composition. They have the same altitude. They have the same optical properties. After a few hours, if you didn't know a plane had passed overhead, you would look up and see what appears to be a perfectly ordinary cirrus cloud. And you would be wrong. These are called contrail cirrus. And here's what should make you sit up. They are not a small effect. Studies using satellite data have found that in heavily trafficked air corridors, particularly over the North Atlantic flight tracks, over Central Europe, and over the eastern United States, contrail cirrus can cover a significant fraction of the sky. Some estimates suggest that contrail cirrus adds as much as 5 to 10% to the total cirrus cloud cover in these regions on busy traffic days. There's a satellite technique where researchers compare cirrus coverage during periods of heavy air traffic with periods of light traffic, or compare areas with dense flight routes to nearby areas with few flights. The signal is clear. More flights, more cirrus. The correlation holds up across multiple studies, multiple regions, and multiple years. The planes are making clouds. On some days in busy air corridors, you can see the entire sky hazed over with a thin milky layer that isn't natural cloud at all. It's aircraft exhaust that has spread and merged and become something that looks indistinguishable from the real thing. Photographers call it milky sky or whiteout. Astronomers hate it because it dims the stars. And climate scientists study it because it changes the energy balance of the planet. So a plane takes off from London, flies to New York, and leaves behind it a line of ice crystals that slowly, over hours, spreads into a sheet of cirrus cloud that covers hundreds of square miles. The plane lands. The passengers get off. They go home. And up in the sky, the cloud that their flight created is still there, quietly changing the way sunlight interacts with the earth. I want you to pause on that, because it means that you, sitting in seat 14C on a Tuesday afternoon, were part of a machine that manufactured weather. Not big dramatic weather, not thunderstorms or hurricanes. Something subtler. A thin, persistent, slowly spreading cloud that might cover your departure city by the time you land at your destination. The plane was a cloud factory, and you were riding inside it. All right, next layer. What does a cloud do? What does any cloud do, physically? This is one of those questions that sounds simple, but opens up a universe of physics. And I want to take some time with it, because everything that follows depends on getting this right. A cloud interacts with electromagnetic radiation. That's what a cloud does. It sits in the sky, and it affects the flow of energy in the form of light through the atmosphere. And it does this in two very different ways, at two very different wavelengths, with two very different consequences. First, a cloud reflects sunlight. Incoming solar radiation, which peaks in the visible part of the spectrum, hits the cloud and some of it bounces back into space. This is a cooling effect. If the cloud weren't there, that sunlight would have reached the ground and been absorbed by the surface, warming it up. The cloud intercepted it and sent it away. This is what thick, low clouds like cumulus do very effectively. A white cloud over a dark ocean is a powerful reflector. It can send back 70 or 80% of the incoming sunlight. That's a lot of cooling. The measure of how much a cloud reflects is called its albedo. The word comes from the Latin for whiteness. A perfect mirror has an albedo of 1. A perfectly black surface has an albedo of 0. Clouds are somewhere in between, but typically on the high side. A thick cumulus cloud might have an albedo of 0.7 or higher. A thin cirrus cloud might have an albedo of only 0.1 or 0.2, meaning it lets most of the sunlight through. This difference matters enormously. Second, a cloud absorbs and re-emits infrared radiation. The Earth's surface, warmed by the sun during the day, radiates heat upward in the form of infrared light. This is the Earth trying to cool itself. The warm surface emits electromagnetic radiation with wavelengths much longer than visible light, typically between 5 and 50 micrometers. A cloud intercepts some of that outgoing infrared and absorbs it. The cloud warms up slightly, and then it re-radiates energy in all directions, including back down toward the surface. This is a warming effect. The cloud acts like a blanket, trapping heat that would otherwise escape to space. You've felt this effect on a cloudy night. Cloudy nights are warmer than clear nights, because the clouds are sending some of the Earth's heat back down. Every cloud does both of these things simultaneously. It reflects sunlight, cooling the surface, and it traps infrared, warming the surface. The net effect depends on which one wins. And which one wins depends on the cloud. For thick, low clouds, the reflection effect dominates. These clouds are close to the surface, so they're relatively warm. Warm objects radiate more infrared energy upward, which partially offsets their blanketing. But they're very white, so they reflect a lot of sunlight. Net result, cooling. Low clouds make the Earth cooler than it would be without them. For thin, high cirrus clouds, and this includes contrail cirrus, the balance tips the other way. The reason is both temperature and transparency. High cirrus clouds are very cold. They sit at temperatures of -40 to -60 degrees. Cold objects radiate very little energy, so a cirrus cloud doesn't radiate much heat upward toward space. But it's very effective at absorbing the much warmer infrared coming up from the surface below and re-radiating some of that energy back down. It's a one-way blanket, good at trapping, bad at releasing. Meanwhile, because it's thin and wispy, it doesn't reflect all that much incoming sunlight. Some of it gets through. The net result: thin, high cirrus warms. The blanket effect wins over the reflection effect, and that applies directly to contrail cirrus. This means contrail cirrus has a net warming effect on the climate. The plane flies over, the contrail forms. It persists because the air is humid. It spreads into cirrus. That cirrus traps more heat than it reflects. The Earth gets a little bit warmer. And the time of day matters enormously. During the daytime, contrail cirrus does both things at once. It reflects some incoming sunlight, cooling the surface, and it traps outgoing infrared, warming the surface. The warming wins, but the cooling partially offsets it. At night, though, there's no sunlight to reflect. The cooling effect disappears completely, but the warming effect persists because the Earth is still radiating infrared heat, and the contrail cirrus is still trapping it. So a contrail formed at night, or one that persists from an evening flight into the nighttime hours, has a stronger net warming effect than the same contrail during the day. This has an immediate practical implication. A relatively small fraction of flights occur at night or during the winter twilight hours. But those flights produce a disproportionately large fraction of the total contrail warming because they produce contrails that trap heat without reflecting sunlight. If you wanted to reduce the climate impact of contrails, one of the most effective strategies might be to focus on night flights. Reroute or reschedule the flights that produce persistent contrails during darkness, and you could eliminate a large chunk of the warming with a relatively small disruption to the flight schedule. How much warming are we talking about? This has been studied intensely over the past 2 decades, and the numbers are startling. A paper published by researchers led by Lisa Bach and Ulrike Burkhardt in 2019 estimated that the warming effect of contrail cirrus is approximately equal to the warming caused by all the carbon dioxide that aviation has ever emitted. Let me say that again. The warming from contrails and the clouds they create may be comparable in magnitude to the warming from all the CO2 from all the jet fuel ever burned by all the aircraft that have ever flown. That's a remarkable result. And it means that when people discuss the climate impact of flying, they often focus on carbon dioxide, because that's the greenhouse gas everyone knows about. But the contrails, the white lines, the things you see when you look up, might be just as important, maybe more important. And here's the twist that makes this actionable rather than just alarming. Unlike CO2, which stays in the atmosphere for centuries once it's emitted, a contrail lasts hours to days, at most a few days. Then the ice crystals sublimate, or precipitate out, and the cloud is gone. This means contrails are a short-lived climate forcer. If you stop making them, the warming effect disappears almost immediately. By next week, the atmosphere has forgotten them. Compare that with CO2, where even if you stopped all emissions today, the CO2 you emitted last year and the year before and 50 years before that is still up there, still trapping heat, and will continue doing so for centuries. This has a stunning practical implication. If you could figure out how to avoid making persistent contrails, you could eliminate roughly half the warming effect of aviation almost overnight. No new engine technology needed. No decade-long development cycle for alternative fuels. Just stop making the long-lived contrails and the benefit appears immediately. And it gets better. Not all flights produce persistent contrails. Most don't. The majority of contrails are the short-lived type that vanish within minutes because the ambient air is dry. Only flights that pass through ice supersaturated regions produce persistent contrails. And those regions are not randomly distributed. They tend to occur in specific weather patterns, at specific altitudes, in specific seasons. Research suggests that a relatively small fraction of all flights, perhaps 10 to 20%, are responsible for the vast majority of the contrail warming effect. 80% of the warming from 2 or 3% of the global flight distance, in some estimates. That's an 80-20 rule for climate damage. A small number of flights, in the wrong place at the wrong time, doing most of the harm. If you could identify those flights in advance and reroute them, just change their altitude by 1,000 feet or shift their path by 50 miles, you could avoid the worst contrails while barely affecting the rest of aviation. But I'm getting ahead of myself. Let me show you another layer. Let's think about why these ice crystals are so effective at trapping heat. And to do that, I need to tell you a little bit about how light interacts with small particles. When electromagnetic radiation, light, encounters a particle, what happens depends on the relationship between the wavelength of the light and the size of the particle. If the particle is much larger than the wavelength, the light bounces off it like a ball off a wall. That's geometric optics. Reflection and refraction. The stuff you learn in high school with mirrors and prisms. If the particle is much smaller than the wavelength, you get what's called Rayleigh scattering. The light barely interacts with the particle, and what interaction there is depends strongly on wavelength. Short wavelengths, blue light, scatter much more than long wavelengths. Red light, that's why the sky is blue. The molecules of nitrogen and oxygen in the atmosphere are much smaller than visible light wavelengths, so they scatter blue light preferentially. But if the particle is roughly the same size as the wavelength, something more complicated happens. You enter the regime described by Mie scattering theory, named after the German physicist Gustav Mie, who worked out the mathematics in 1908. In this regime, the light scatters in complex patterns that depend sensitively on the exact ratio of particle size to wavelength. The particle acts as a tiny antenna, absorbing the incoming electromagnetic wave and re-radiating it in patterns that can be calculated but are rich and intricate. The scattering is roughly equal across all visible wavelengths, which is why clouds look white rather than colored. White means all wavelengths are being scattered with similar efficiency. The ice crystals in contrails are typically on the order of a few micrometers to a few tens of micrometers in size. Visible light has wavelengths of roughly 0.4 to 0.7 micrometers. So the crystals are several times to perhaps 50 times larger than visible wavelengths. They're solidly in the Mie regime for visible light. They scatter it effectively and approximately equally across wavelengths. This is why contrails are white. But here's the key. Infrared radiation, the heat radiation emitted by the Earth's surface, has much longer wavelengths. Typical thermal infrared is in the range of 5 to 50 micrometers. And now the ice crystals, which are a few to a few tens of micrometers, are comparable in size to these infrared wavelengths. That means they interact very strongly with infrared light. They absorb it efficiently and re-emit it in all directions, including downward back toward the surface. This is the physics that makes Contrail cirrus a warming agent. The ice crystals are in a sweet spot of size, big enough to interact strongly with outgoing infrared, small enough that there aren't enough of them in a thin cirrus sheet to block a huge amount of incoming sunlight. The infrared trapping wins, the blanket effect dominates, and the size of the ice crystals matters. Contrail ice crystals tend to be smaller than the crystals in natural cirrus clouds. Natural cirrus crystals have had more time to grow by collecting water vapor from the surrounding air. They can reach sizes of hundreds of micrometers or even larger. Contrail cirrus crystals, because they form quickly around soot particles and spread before they have time to grow very large, tend to be smaller. And smaller crystals, for a given mass of ice, mean more crystals. More crystals means more total surface area. More surface area means more interaction with infrared radiation. So contrail cirrus, crystal for crystal, is actually more effective at trapping heat than natural cirrus. The soot seeds produce a cloud that is in a sense optimized for warming, not on purpose, but by accident of the physics. Let me add yet another layer, because the story of soot isn't finished. Remember those soot particles at the core of each ice crystal? They matter beyond just being seeds for condensation. The number of soot particles determines the number of ice crystals, and the number of ice crystals determines the optical properties of the contrail. If you could reduce the number of soot particles in the exhaust, you'd get fewer but larger ice crystals. Fewer crystals means less total surface area. Less surface area means less infrared absorption, less warming. This is one reason people are excited about sustainable aviation fuels. These fuels, made from things like waste cooking oil, plant-based feedstocks, or even captured carbon dioxide converted into hydrocarbons, burn cleaner than conventional kerosene. They produce less soot, substantially less. Tests have shown that engines burning a blend of sustainable aviation fuel produce up to 50 to 70% fewer soot particles than engines burning standard Jet A fuel, and the contrails they create have fewer, larger ice crystals. The contrails still form, because you're still burning hydrogen and carbon in cold air, but they're optically thinner. They trap less heat. One study, led by Christian Voigt and colleagues, flew research aircraft behind commercial jets that were burning different fuel blends. They measured the properties of the contrails directly, flying through them with particle counters and spectrometers. They found that a 50-50 blend of sustainable aviation fuel reduced the number of ice crystals in the contrail by 50 to 70%. Fewer crystals means less total surface area interacting with infrared radiation. The warming effect dropped accordingly. Think about what that means. You didn't change the route. You didn't fly lower. You didn't avoid the humid air. You just changed what went into the tank, and the contrails became less harmful. Not because you made fewer of them, but because you changed the microphysics inside them. Fewer soot seeds, fewer ice crystals, larger crystals, thinner optical cloud, less warming. The physics works in your favor if you understand it deeply enough. There's a certain satisfaction in that. The same physics that creates the problem, soot nucleation and ice crystal optics, also provides the solution. You don't need to invent new physics. You just need to change one input, the number of soot particles, and the entire cascade of consequences shifts. That's the power of understanding a system from the bottom up. Once you know where the leverage point is, you can move it. There's another approach being tested right now. Route optimization. If you know where the humidity is high enough to produce persistent contrails, you can reroute flights to avoid those regions. This means flying a slightly longer path, burning a tiny bit more fuel, and emitting a tiny bit more CO2. But the trade-off is overwhelmingly worth it, because the warming you avoid by preventing a persistent contrail can be many times larger than the warming caused by the extra fuel. Let me put numbers on this. A typical diversion to avoid a contrail-forming region might add 1 to 3% to the fuel burn on that flight. That means 1 to 3% more CO2. But the persistent contrail you avoided might have produced a warming effect 10 to 100 times larger than that extra CO2, depending on how long the contrail would have persisted and how much it would have spread. The math is lopsided, overwhelmingly in favor of avoidance. Several airlines have already run test programs. Flights equipped with real-time atmospheric data, including humidity and temperature profiles at various altitudes along the route, were given optimized flight plans that avoided the worst ice-supersaturated regions. The pilots changed altitude by as little as 2,000 feet, and satellite imagery confirmed that the contrails either didn't form at all or dissipated rapidly. The flights used slightly more fuel, but the net climate impact was dramatically lower. The challenge is prediction. You need very accurate atmospheric data, humidity and temperature at specific altitudes along the flight path, updated in real time. That's a hard meteorological problem. Weather models are good at predicting temperature at altitude. They're much worse at predicting humidity, especially the fine-grained humidity variations that determine whether a specific patch of air is supersaturated with respect to ice. A patch of supersaturated air might be a few kilometers across. If your weather model has a resolution of 50 kilometers, you might miss it entirely. Or predict one where none exists. This is an area where satellite observations, high-altitude weather balloons, and machine learning are all being brought to bear. Researchers are training models on years of satellite data, flight track data, and atmospheric measurements to predict where persistent contrails will form with better and better accuracy. It's not a solved problem, but it's a solvable one. And the payoff for solving it is enormous, because it unlocks a way to cut aviation's climate impact in half without grounding a single plane. Let me take you one more step deeper, because there's something genuinely beautiful hiding in all of this that I don't want you to miss. Everything we've talked about, the condensation, the freezing, the soot nucleation, the crystal growth, the spreading, the infrared trapping, all of it comes down to one substance. Water. Just water, in 3 of its phases. The exhaust contains water vapor. That's the gas phase. The vapor condenses into droplets. That's the liquid phase. The droplets freeze into ice crystals. That's the solid phase. And the transitions between these phases, vaporization, condensation, freezing, sublimation, are governed by thermodynamics, by the relationships between temperature, pressure, and the energy stored in molecular bonds. When water vapor condenses into a droplet, it releases energy. Latent heat. The same latent heat that makes steam burns so dangerous. When a droplet freezes into ice, it releases more energy. The latent heat of fusion. These energy releases are what keep ice crystals warm enough to persist in an environment that is otherwise brutally cold. The crystal releases heat as it grows, and that released heat slows the cooling of the surrounding air, creating a delicate local equilibrium where the crystal can survive. And when you zoom into the ice crystal itself, you find something wonderful. The water molecules in an ice crystal arrange themselves in a hexagonal lattice. Each oxygen atom sits at the center of a tetrahedron of neighbors, bonded by hydrogen bonds at specific angles. This hexagonal symmetry is why snowflakes have six-fold symmetry. It's why ice floats, because the hexagonal lattice is more open than liquid water, making ice less dense. And it's why the surface of an ice crystal has particular properties that make it extraordinarily good at capturing water vapor from the surrounding air. The surface of an ice crystal is not quite solid and not quite liquid. There's a thin layer, just a few molecules thick, that has the disordered structure of liquid water even at temperatures far below freezing. This quasi-liquid layer was first proposed by Michael Faraday in 1850, based on nothing more than careful observation and intuition. He noticed that when you press two pieces of ice together, they stick. They fuse. Faraday reasoned that there must be something liquid-like at the surface that allows this bonding to occur. He was right, though it took more than a century of experimental physics to confirm his intuition and measure the layer directly. The quasi-liquid layer is one of the most interesting things in surface physics. It exists because the molecules at the very surface of an ice crystal don't have neighbors on all sides. They have neighbors below them and to the sides, but above them is empty air. This asymmetry means the surface molecules are less tightly bound than the molecules deeper in the crystal. They have more freedom to move around. They oscillate and shift and rearrange almost like liquid molecules, even though the bulk of the crystal is rigidly solid. The layer is typically only a few nanometers thick, but its effects are profound. This quasi-liquid layer is why ice is slippery. It's why skating works. For a long time, people thought the pressure of the skate blade melted the ice, but the numbers don't work out. The pressure from a skate blade isn't nearly enough to lower the melting point significantly. What actually happens is that the quasi-liquid layer is already there, and the blade glides on it. And it's relevant to contrails because this layer is what allows water molecules from the surrounding vapor to attach smoothly to the crystal surface and be incorporated into the growing lattice. A water molecule arriving from the vapor phase lands on the quasi-liquid layer, diffuses across it, finds a favorable spot on the crystal lattice, and snaps into place. Without this mobile, liquid-like layer mediating the process, crystal growth would be much slower and would proceed in a very different fashion. The contrails would have different crystal shapes, different optical properties, and a different climate effect. A thin layer of disordered molecules, a few nanometers thick, on the surface of a crystal, a few micrometers across, inside a contrail a few meters wide, from a plane 35,000 feet up, is affecting the energy balance of the planet. I defy you to find a more dramatic example of small things mattering. All of this, from a white line in the sky. You started by looking up and seeing a chalk mark. And inside that chalk mark is combustion chemistry, gas phase thermodynamics, aerosol physics, ice nucleation, crystal growth kinetics, surface physics, radiative transfer, and climate science. Each layer was hiding underneath the previous one, waiting for you to look more carefully. That's what I love about physics. You can start anywhere. You can start with the most mundane, obvious, boring thing you can think of, a white line in the sky that you've seen 1,000 times, and if you keep asking why and how and what's really going on, you end up somewhere astonishing. You end up at the molecular structure of ice. You end up at the energy balance of the entire planet. You end up discovering that a Tuesday afternoon flight from Chicago to Denver might warm the Earth more by the cloud it leaves behind than by the fuel it burns. Let me tell you one more thing, and then I'll let you go. During the days immediately after September 11, 2001, when all commercial air traffic over the United States was grounded, something unprecedented happened. For the first time since the dawn of the jet age, the skies over the continental United States were completely free of contrails. No planes meant no exhaust. No exhaust meant no soot. No soot meant no ice crystals. No ice crystals meant no contrail cirrus. For 3 days, Americans looked up and saw a sky that no living American had ever seen. The natural sky, unmodified by aviation, pure and sharp and vivid. A climate researcher named David Travis had been studying contrails for years. He had spent his career measuring their properties, tracking their spread from satellite imagery, calculating their radiative effects. And suddenly, nature handed him the perfect experiment. A controlled study that no ethics board would ever approve, and no funding agency would ever pay for. Ground every plane in the country and see what happens to the climate. Travis and his colleagues measured the difference in daily temperature range, the spread between daytime highs and nighttime lows during those 3 days of clear skies. And they found something striking. The daily temperature range increased by roughly 1 degree Celsius compared to the average. The days got a little warmer and the nights got a little cooler, because the contrail cirrus blanket was gone. The blanket that normally traps heat at night and slightly dims the sun during the day was absent, and the temperature responded accordingly. Think about what that tells you about the sky you normally see. On an ordinary day in the United States, with tens of thousands of flights crossing the continent, the sky above you is not the sky your grandparents saw. It's been modified. The natural cirrus is supplemented by artificial cirrus, created by aircraft exhaust, hanging at 30 to 40,000 feet, subtly changing how much sunlight reaches the ground and how much heat escapes to space. You live under a different sky than the one that existed before the jet age. Not dramatically different. You can't see the difference with your naked eye on most days. But the instruments see it, and the climate responds to it. There's a caveat. 3 days is a very short sample. The weather during those specific days might have been unusual for other reasons. Travis himself was careful about this. Later analyses have debated how much of the signal was really from contrails and how much from natural weather variability. The scientific community hasn't reached full consensus on the magnitude. But the basic physics is sound. Contrail cirrus traps heat. Remove it, and the atmosphere responds. The September 11th natural experiment was imperfect, but it pointed in exactly the direction the physics predicts. And it raised a provocative question that researchers are still grappling with. We know how to stop making contrails. Ground the planes. We did it for 3 days, involuntarily. The question is whether we can get most of the benefit without grounding anything. Whether we can keep flying but fly smarter, with cleaner fuels and optimized routes that avoid the worst ice supersaturated regions. Whether we can unweave the artificial cirrus from the natural cirrus and give back something closer to the original sky. The answer seems to be probably yes. At least partially. But it requires something that hasn't traditionally been part of aviation planning. It requires treating the atmosphere not just as empty space that planes fly through, but as a reactive medium that the plane transforms on its way through. Every flight is an atmospheric experiment, whether we acknowledge it or not. The question is whether we want to run those experiments blindly or with some awareness of what we're doing to the air. And that brings us back to where we started. You looked up. You saw a white line. And now you know what it is. It's your breath, on a cold morning, scaled up by a factor of 1,000,000. It's a chemical reaction producing water and soot. It's a cloud factory. It's a planetary blanket. It's a climate-forcing agent that might rival all the CO2 aviation has ever produced. And it's something we might be able to fix, not by grounding flights, but by changing the fuel we burn and the routes we fly, using the same physics that created the problem in the first place. Let me step back and appreciate something about the structure of what we just did. We started with a white line, just a white line, a thing you've seen thousands of times and probably never spent more than half a second thinking about. And we peeled it, layer after layer. Condensation, humidity, ice supersaturation, soot nucleation, crystal microphysics, cloud formation, radiative transfer, climate forcing, sustainable fuels, atmospheric routing. Each layer was sitting inside the previous one, quiet and patient, waiting to be noticed. That's what the physical world is like. It's not divided into simple things and complicated things. Everything is complicated, if you look closely enough. And the things that seem most ordinary, the things you see every day and dismiss because they're familiar, are often the richest. A white line in the sky, a glass of water, a shadow on the wall, the squeak of a shoe on a gym floor. Each one of them is a doorway to an enormous edifice of physics, and most people walk past those doorways every day without ever looking inside. I think the best physics education doesn't start with equations on a blackboard. It starts with somebody pointing at something ordinary and saying, "Have you ever really looked at that?" Because once you really look, once you ask the first honest question, you can't stop. Each answer spawns 3 more questions. Each layer reveals another layer underneath. And pretty soon, you're standing in the middle of a cathedral of understanding that was built one why at a time, starting from a single white line in the sky. A white line in the sky. You've seen it 10,000 times and never thought twice. But inside that line is a physics lesson that connects combustion chemistry to cloud microphysics, to radiative transfer, to the energy balance of the entire planet, all in a trail of ice that a plane left behind 20 minutes ago. Next time you look up and see one of those lines, I want you to actually look at it. Watch how it behaves. Is it vanishing fast? Then the air up there is dry. Is it spreading slowly, getting wider, turning fuzzy at the edges? Then the air is humid, and you're watching a cloud being born in real time. Watch which direction it drifts. That's the wind shear at 35,000 feet, made visible. Watch how it thins in some parts and thickens in others. That's turbulence. That's the atmosphere breathing. You're watching the invisible structure of the upper atmosphere revealed by a line of ice crystals, like iron filings showing you a magnetic field. The sky is telling you its secrets, and the only equipment you need is your eyes. You're watching physics happen. In real time. For free. Written in water and ice and sunlight across the biggest canvas there is. Tell me, next time you see a contrail spreading across the sky and hanging there long after the plane has gone, what will you think about? I'd like to know.